You know that feeling when you're trying to make sense of a chaotic situation. Maybe there's just too much information, too much noise, and you just can't seem to see the signal through all the static. That's precisely what many of our most critical technologies, especially in medicine, face every single day. They're trying to interpret the body's subtle messages amidst all that chaos. Today, we're embarking on a deep dive into the fascinating world of digital filter design. Think of it as like the ultimate cleanup crew for data. It allows us to extract crystal clear insights from even the messiest signals the human body throws at us. Our mission to unpack how these digital wizards work, why they're so crucial in biomedical applications, and maybe uncover some surprising facts beneath their complex sounding names. We're drawing from an incredibly comprehensive guide, Biomedical Digital Signal Processing by Willis J. Tompkins. It's really a treasure trove of knowledge, bridging that gap between, theoretical signal processing and its life-changing applications.
Exactly. And for you, our curious listener, we really aim to provide not just the what, but the why these techniques matter. We want to give you those aha moments without getting bogged down in overwhelming mathematical detail. This is about making you truly well-informed on a topic that touches everything from the heart monitor in the ICU to really advanced diagnostics. It profoundly shapes how we understand and interact with the human body's most intricate signals.
Okay, let's start at the beginning then. Imagine a raw, messy signal coming from, say, your heart, picked up by an electrode. Before we had all this computing power, we used analog filters, right? Physical circuits trying to smooth things out directly on the electrical wave. But they had limits, didn't they? What were the big problems with those analog approaches that pushed us towards digital?
That's a great starting point because it really highlights the fundamental shift. Analog filter, yeah, they worked, but they're inherently prone to drift. Their characteristics would change, with temperature fluctuations, components getting old, and once you built one, it was really hard to precisely control or modify it.
Right, like you couldn't just software update it.
Exactly. Imagine trying to tweak a filter in a device already hooked up to a patient. You'd literally have to open it up, swap out physical resistors or capacitors.
Mm.
Impractical. Now, what's truly fascinating is the shift to digital. Instead of operating on those continuous electrical waveforms, digital filters operate on sequences of numbers. These numbers represent the waveform.
So we turn the physical thing into data first.
Precisely. We've taken the physical world, converted it into data, and now we process that data mathematically using software. And here's the key insight. Digital filters are inherently more immune to noise, and they're far, far more precise. Their accuracy depends only on the number of bits the designer chooses. That gives them incredibly predictable behavior.
So you control the error much better.
Much better. You essentially control the round-off error. This isn't just a different way of doing things, it's a complete game changer. It offers unparalleled flexibility and stability.
Right.
And that precision, that adaptability, it's absolutely vital in places like an intensive care unit computer. An ICU system has to acquire, recognize, and report on patient signals in real time, often, literally, with life or death implications. You can't have filters drifting or giving unreliable readings there.
Okay, so this shift to digital, with all its benefits, stability, precision, flexibility, it didn't just happen in a vacuum, right? What was the big catalyst? What made this digital revolution not just possible, but, well, everywhere?
The foundation for this whole digital transformation lies squarely with the evolution of the microprocessor. And that advancement is beautifully captured by Gordon Moore's famous observation, Moore's Law.
Right, the doubling of transistors.
Exactly. He noted way back in 1965 that the number of functional transistors you could fit on a single piece of silicon roughly doubles every 2 years. Or maybe it was 18 months. The exact period shifted a bit, but the trend held. And the incredible thing is, this exponential growth has continued exceptionally well for decades. It's been remarkably consistent. Think about it. You go from the Intel 4004 in 1971, which had, about 2,000 transistors?
Tiny by today's standards.
Absolutely tiny. Then, just a couple of decades later, you get chips like the Intel i486 or the Motorola 68040, boasting over 1 million transistors. And that relentless progress hasn't stopped. We're talking billions now. For you, our listener, this translates directly into continuously increasing computing power and memory. And it's all packed into smaller, cheaper, and lower power consumption packages.
Which is huge for medical devices.
Yeah, huge, especially for portability. This allowed for the development of new medical instruments, particularly portable ones, that were just inconceivable before, things you couldn't build because they'd be too big, too expensive, or need too much battery power. Now, it's interesting. While the human brain, with its vast network of neurons, still holds an edge in sheer complexity and, associative memory, a standard PC, even back then, could perform basic computational tasks, like adding numbers, but 1,000,000 times faster than a human.
Wow, 1 million times faster.
Yeah. And the power of digital signal processing lies in exploiting this immense computational speed advantage. It allows us to perform these complex calculations on physiological data with unprecedented speed and accuracy, right where and when it's needed, like at the patient's bedside or even in a wearable device.
Wow. Okay, so the processing power caught up. But before any of these digital filters can even get to work their magic, we have that fundamental step. We have to bridge the gap between our messy, continuous analog world, like a heartbeat, and the neat, organized digital realm of numbers. How do we actually do that? How do we
Yeah.
turn that continuous wave into a string of numbers a computer can understand?
That is the critical first step. Absolutely. And it all starts with sampling.
Right.
Essentially, we take discrete amplitude values, snapshots, if you will, of a continuous signal at regular, precisely timed intervals.
Like frames in a movie.
Kind of like that, yes. Think of it like taking a series of photos of a moving object at fixed moments in time. For an electrocardiogram, an ECG, we might take, say, 200 snapshots or samples every second. Now, theoretically, there's a golden rule here, Shannon's sampling theorem. It tells us that if we know the highest frequency present in the signal we care about, we can perfectly reconstruct it later. But only if we sample at a rate at least twice that highest frequency. That rate is called the Nyquist frequency.
Okay, so sample at least twice as fast as the fastest thing you want to see.
Exactly. The key insight is you need enough snapshots to capture all the essential detail, all the wiggles and variations in the signal.
That makes sense. Sample fast enough? But what happens if we don't? Because, like you said, real-world signals, especially from the human body, they're never perfectly clean, are they? There's always noise.
Precisely. Real-world signals are almost always corrupted by noise. And this noise often contains frequencies higher than the actual signal we're interested in. Imagine an ECG electrode placed over a muscle. It can easily pick up unwanted electrical signals from the muscle firing that's electromyographic, or EMG, noise. And EMG signals can be much faster, much higher frequency than the heart's electrical activity.
Okay, so you've got the heart signal plus this faster muscle noise all mixed together.
Right. Now, if your sampling rate is too low, lower than twice the frequency of that muscle noise, or if you have a non-ideal low-pass filter at the input, what we call an anti-aliasing filter, that allows those high noise frequencies to slip through before sampling, then those higher frequencies get misrepresented. They fold over or alias and appear as lower frequencies in your sample data.
So the noise pretends to be part of the signal you wanted.
Exactly. It's insidious because it irrevocably corrupts the signal. Once aliasing happens, you can't undo it. You can't distinguish the true signal from the alias noise anymore. It's like trying to understand a phone call where high-pitched sounds randomly get replaced by low-pitched ones. You simply can't recover the original meaning.
Okay, so anti-aliasing filters before sampling are critical.
Absolutely critical. You need to remove those potentially troublesome high frequencies before you sample. And furthermore, even at the output stage, when we want to convert the processed digital data back into an analog signal, perhaps for display on a monitor, the output filter, sometimes called a reconstruction filter, must also be carefully designed. It needs to smooth out the steps from the digital conversion and exclude undesired high-frequency components, called repeated spectra, that mathematically appear in the digital signal representation. Otherwise, the reconstructed analog signal will still contain distortions.
All right, so we've taken our snapshots, our discrete samples, hopefully without aliasing. But what are the actual pieces of hardware, the components that perform this crucial translation between the continuous analog world and the computer's binary language, and then back again if needed?
These are the workhorses: the analog to digital converters, or AD converters, and the digital to analog converters, or DA converters. They are the indispensable interfaces, the translators. They allow continuous signals to speak the binary language of computers and then translate that digital language back into continuous understandable signals. Let's look at DA converters first. They go from digital numbers back to analog voltages or currents. Their objective is simple: construct an analog output signal from a given digital input number. The core idea is to take that digital number and accurately scale a very stable reference voltage to produce a corresponding analog voltage level. This scaling is usually done using precise resistor networks like an R2R ladder or sometimes capacitor arrays.
So each number corresponds to a specific voltage level.
Exactly. Now, simple DA converters produce discrete voltage steps. It looks like a staircase if the digital input is ramping up. To reconstruct a smooth analog signal from these steps, we use interpolation techniques. The simplest is a zero-order hold, which just holds the voltage level until the next sample. Or you can use linear interpolation, drawing straight lines between the points, or even more sophisticated band-limited interpolation for better accuracy.
And the quality of that DA matters, right? Especially in medicine.
Hugely. Think about things like integral linearity and differential linearity. These aren't just abstract technical specs. Integral linearity ensures that the output voltage is truly proportional to the digital input across the whole range. Differential linearity ensures that the step size between adjacent digital codes is uniform. For something like a precision drug infusion pump controlled digitally, that linearity isn't just nice to have, it's the guarantee that a digitally commanded dose translates into the exact analog flow rate the patient needs.
A tiny deviation could be critical.
Absolutely. It could have serious implications. So these metrics, linearity, monotonicity, ensuring the output never decreases when the input increases, resolution, the smallest step size, they're central to patient safety and reliable medical device operation. Now, AD converters do the opposite job. They determine the digital word, the binary number that represents a given analog input voltage. For rapidly changing signals, an AD converter often needs a helper circuit right at its input, a sample and hold circuit.
Why is that needed?
Because the AD conversion process itself takes a short but finite amount of time. If the analog input voltage changes during that conversion time, the resulting digital number will be inaccurate. The sample and hold circuit essentially takes a very quick snapshot of the analog voltage and freezes it, holding it steady while the main AD converter does its work. This ensures a stable input for the duration of the conversion. There are several different types of AD converters, each representing a clever engineering trade-off between speed, accuracy, cost, and hardware complexity. It's always a balance. For instance, there's the counter type, which is simple but slow. It just increments a counter, converts that count to an analog voltage using an internal DA, and stops when that voltage matches the input. Conversion time depends on the input signal level.
Okay, simple, but maybe not fast enough for everything?
Right. Then you have the dual slope converter. It works by integrating the input signal for a fixed time, then integrating a reference voltage in the opposite direction until it gets back to zero. It's known for being highly accurate because its output isn't directly dependent on the exact values of the integration components or the clock rate. Those factors tend to cancel out. It's also excellent at averaging out high-frequency noise that might be riding on the input signal, often chosen when meticulous precision is absolutely non-negotiable, maybe for precision measurement instruments, even if it's a bit slower.
So, accuracy over speed.
Often, yes. Then there's the successive approximation converter. This is a very common type, a real workhorse. It works more like a guessing game. It compares the analog input to a series of internal voltage references generated by an internal DA, essentially determining the correct digital output bit by bit, starting from the most significant bit down to the least significant. For an n-bit converter, it typically takes n clock cycles. It offers a good balance of speed, resolution, and cost for many biomedical applications.
A good all-rounder.
Pretty much. And finally, for sheer speed, you have the parallel or flash converter. This is the drag racer of AD converters. It uses a whole bank of comparators, 2n1 comparators for an n-bit word to compare the input voltage to all possible quantization levels simultaneously. This allows it to determine the digital output in basically a single clock cycle. It's incredibly fast.
But I bet it's complex and expensive.
You bet. The speed comes at the cost of significantly more complex hardware, higher power consumption, and typically lower resolution compared to other types for the same cost. It's used when bandwidth is absolutely critical, like in digital oscilloscopes or high-speed data acquisition. Often, the limiting factor for its speed isn't the conversion itself, but how quickly the sample and hold circuit can acquire the signal. The key, again, is understanding these trade-offs. Speed, accuracy, complexity, cost. Choosing the right AD depends entirely on what the specific medical application demands. And one last piece here. For applications where you need to monitor multiple physiological signals, like maybe several ECG leads, temperature, pressure, instead of having a separate AD converter for each one, which can get expensive, especially for the typically low-frequency biomedical signals, you can use an analog multiplexer. Think of it as an electronic switch. It directs the various analog input signals sequentially to a single shared AD converter.
So one AD handles multiple inputs, one after the other.
Exactly, it cycles through them. This saves considerably on hardware and cost, and it's perfectly adequate for many biomedical signals that don't change extremely rapidly.
Okay, that makes sense. We've gone from the analog world, sampled it carefully, avoided aliasing hopefully, and used an AD converter to turn it into digital numbers. But given all that initial complexity, why do we bother? We touched on the advantages, but let's revisit. Why are digital filters still the undisputed go-to choice? especially when lives might be on the line in medical devices. What makes them so compelling?
It's a really critical question. And the advantages, they really do bear repeating because they are so profound. They address fundamental challenges in getting reliable information from signals. First and foremost, as we said, is their inherent immunity to noise compared to analog circuits, and their highly predictable accuracy. Remember that accuracy is directly determined by the number of bits you choose for representing the numbers. This gives designers precise control over any potential round-off errors. Very predictable.
Unlike analog parts that can drift.
Exactly. Unlike their analog counterparts, which can subtly change their characteristics over time due to component aging, or with temperature fluctuations. Imagine a filter in an ICU room getting slightly warmer and changing its cutoff frequency. That doesn't happen with digital filters. They don't drift. Once you implement them in software, their behavior is fixed and reliable. And that leads to the next huge advantage: unparalleled flexibility.
Easy to change the software.
Much easier. They can be easily modified, upgraded with better algorithms, or even completely reconfigured for different tasks just by changing the software code. You don't need to touch any physical hardware. This stability, this adaptability, and this unwavering precision, they are absolutely paramount in medical instrumentation. Reliability and the ability to refine performance without physical intervention are critical, often directly impacting patient safety and the accuracy of diagnoses.
Okay, so they're stable, precise, flexible. Got it. But if a digital filter is just manipulating numbers flowing through a computer system, how does the computer actually do the filtering? What are the basic moves, the fundamental mathematical operations it makes to achieve these complex signal transformations?
Right, this is where it gets elegantly simple, almost surprisingly so. The aha moment here is that at its core, any digital filter, no matter how sophisticated its function seems, relies on just three deceptively simple operations that any computer or microprocessor can easily execute. Number one, storage, or what we often call a delay block. This operation simply stores a number, a single sample value for one clock period, one sampling interval t. It makes that past value available for a later calculation.
Like remembering the previous sample.
Exactly. Mathematically, in the analysis domain we use called the Z-transform, this delay is represented as Z1. Think of the Z-transform as a specialized mathematical lens, like the Fourier transform for frequency, but tailored for discrete time systems. It helps engineers analyze and design digital filters more easily. In terms of hardware, a microprocessor just does this by placing data points into memory locations for later recall. It's like holding on to a previous heart rate measurement for a specific duration to compare it to the current one. Number two, multiplication by a constant. This operation instantaneously, or at least very quickly within the clock cycle, multiplies an input number by a fixed predetermined constant, a coefficient. Ideally, there's no delay or storage involved in this step itself. It's a direct scaling of the numerical value, perhaps amplifying a frequency band or attenuating another.
Just scaling the number up or down.
Precisely. And number three, addition. This operation instantaneously sums two or more numbers together. Again, ideally this happens without any delay, you're just combining values, and the significance of these three operations, store, delay, multiply, add, is profound. From these three fundamental building blocks, all the immense complexity and sophistication of digital filtering is constructed. It's like the universal Lego set for signal processing.
Wow, just those three.
Just those three. It means that any general-purpose microprocessor, if it's fast enough, can perform these operations and therefore implement virtually any digital filter in real time. If the microprocessor can complete all its arithmetic, the multiplications and additions for one input sample before the next sample arrives, within one sampling period, t, then we can consider those operations to happen in zero time relative to the signal flow. That enables real-time processing, which is absolutely crucial for monitoring patient vitals or reacting instantly to changes. It's elegantly simple, yet infinitely powerful.
Okay, simple building blocks, but they build complex things. You often hear engineers talk about filter stability. That sounds technical, but clearly vital. What exactly does stability mean in practical terms, and why is it so absolutely critical, especially for a medical device that's analyzing, say, my heartbeat?
Filter stability is absolutely paramount. You cannot overstate its importance, especially for certain types of digital filters that use feedback. We'll get to those, the IR filters. An unstable filter is, quite frankly, a dangerous filter in medical applications because it can produce an output that grows without bound, exponentially increasing.
So the numbers just get bigger and bigger, uncontrollably.
Exactly. Imagine a heart monitor where the filtered signal suddenly starts uncontrollably escalating towards infinity, giving completely meaningless or even terrifyingly alarming false readings. it's a critical error. It could lead to misdiagnosis, inappropriate treatments, alarms going off constantly. The filter becomes worse than useless. It becomes actively harmful. It needs to be reliable. To truly understand and ensure stability, engineers use a conceptual tool called the Z-plane. Imagine it as a kind of architectural blueprint for the filter. It's a two-dimensional mathematical space where we can visualize the filter's characteristics by plotting specific points related to its behavior.
A map of the filter's properties.
A map, exactly. And drawn on this map, this Z-plane, is a critical boundary, the unit circle, a circle with a radius of 1 centered at the origin. Now, for a digital filter to be stable and predictable, meaning its output will always remain bounded, always well-behaved, never run away to infinity, there's a strict rule. All its poles, which you can think of as the filter's inherent resonance points or frequencies where it might naturally want to oscillate, must lie either inside or precisely on this unit circle.
Inside or on the circle. Okay.
And if any poles are exactly on the unit circle, they must also be simple, meaning they aren't repeated roots at the same location. If you have repeated poles on the unit circle, the output can still grow, just linearly instead of exponentially, which is still usually unstable for practical purposes. Interestingly, the zeros of the filter, which represent frequencies the filter strongly attenuates, do not influence stability. Zeros can be located anywhere in the Z-plane, inside, outside, or on the unit circle.
So stability is all about the poles.
It's all about keeping those poles inside, or, carefully, on the unit circle. This fundamental rule guides filter designers, ensuring their digital systems will always produce predictable bounded outputs, which is, of course, non-negotiable for any reliable biomedical instrument. Any angle around the origin in the Z-plane, often represented by the Greek letter theta, specifies a point on this unit circle, relating directly to frequency.
Okay, that makes sense. Poles inside or on the circle means stable, predictable behavior. Got it. So with those foundational digital tools, delay, multiply, add, and the stability rule in our minds, let's dive into the two major families, the main architectures of digital filters that designers choose between. First up, you mentioned FIR filters. What makes them unique, and why are they so widely used, especially in critical applications like medicine?
Right. FIR stands for finite impulse response. And the finite part is the key here. It means their output at any given time depends only on the present input sample and a finite number of past input samples. Critically, FIR filters have no feedback loops. No past output values are ever fed back into the calculation. It's a purely feed-forward structure.
So the output doesn't affect future outputs.
Exactly. And this architectural choice leads directly to several very, very desirable characteristics, especially for medical signals. First, inherent stability. Because there's no feedback, errors or internal numerical oscillations are never fed back into the filter and potentially amplified. This means FIR filters are always stable, guaranteed. That's a huge design advantage, especially in safety-critical systems. You just don't have to worry about the output spiraling out of control, ever.
That's a big weight off the designer's mind.
A huge weight.
Yeah.
Second, and this is really critical for many biomedical signals, linear phase response. This means that all the different frequency components present in the signal are delayed by the exact same amount of time as they pass through the filter.
Why does it matter so much?
It matters because it preserves the shape of the waveform. Think about an ECG again. You have those distinct features, the P wave, the QRS complex, the T wave. Their shapes, their widths, their relative timing. They all contain vital diagnostic information. Linear phase ensures that the filter doesn't distort these relationships. All parts of the wave are shifted in time together, maintaining the morphology. Phase distortion, which happens in nonlinear phase filters, could stretch some parts of the wave and compress others. It could, for example, make a normal unipolar T wave appear biphasic, going both up and down, potentially leading a doctor to misdiagnose a serious cardiac event.
Wow, okay, so preserving the shape is crucial for interpretation.
Absolutely crucial for things like ECGs. Third, FIR filters have predictable finite length register effects. Errors related to quantization, representing values with limited precision, and round-off, errors during calculations, are much less significant and far easier to analyze compared to filters with feedback. Because there's no feedback loop, these small numerical errors don't get propagated, accumulated, and potentially amplified over time.
Easier to manage the small numerical errors.
Much easier. And finally, there's generally ease of design. There are many well-established and straightforward techniques for designing FIR filters to meet specific frequency response requirements, like low pass, high pass, and guarantee that linear phase property. Methods like the window design method or frequency sampling are common, and many software packages automate this process, making them relatively simple to implement reliably. Now, they do have one main trade-off. FIR filters tend to have a slower roll-off compared to the other main time.
Roll-off, meaning how quickly they cut off unwanted frequencies.
Exactly. Roll-off describes how sharply the filter transitions from passing frequencies to blocking them. FIR filters generally need more processing, specifically more coefficients or taps, which means more multiplications and additions and storing more past inputs, to achieve a very sharp, steep cutoff compared to an IIR filter of similar sharpness. So for applications needing extremely sharp frequency selectivity, a high-order FIR filter might become computationally intensive, requiring more processing power or potentially introducing more delay.
So stability and linear phase come at the cost of potentially more computation for sharp cutoffs.
That's the essential trade-off, yes. They can be implemented using direct convolution, basically applying the filter equation directly, or for very long filters, techniques like fast convolution using the fast Fourier transform, FFT algorithm, can offer significant computational savings.
Okay, so that's FIR, stable, linear phase, easy to design, but maybe computationally heavier for sharp cutoffs. What about the other side of the coin, IIR filters? What's their deal, and what are the fundamental trade-offs involved there?
Right. IIR stands for Infinite Impulse Response, and the name hints at the key difference. Unlike FIR filters, the output of an IIR filter depends not only on present and past inputs, but also on past output values. This means they inherently incorporate feedback loops. Past results are fed back into the calculation of the current result.
Okay, so feedback is the big difference. How does that change things?
It fundamentally alters their behavior and characteristics, leading to a different set of pros and cons. Their biggest strength, and often the primary reason they're chosen, is sharp roll-offs with efficiency. IIR filters can achieve much sharper, steeper frequency cutoffs with significantly fewer coefficients, fewer multiplications, additions, and delays compared to an FIR filter achieving the same level of sharpness.
So they're more computationally efficient for the same filtering power.
Generally, yes, especially when you need very sharp transitions between pass bands and stop bands. This means potentially less hardware, lower power consumption, and faster processing for a given filtering requirement. That efficiency can be really attractive, but, and this is big but, there's the potential for instability. Because of those feedback loops, if an IIR filter is improperly designed specifically, if its poles lie outside that unit circle in the Z-plane we talked about, it can become unstable. The output can grow without bound.
So the stability isn't guaranteed like with FIR?
Not at all. It requires careful design, rigorous analysis, and often more complex mathematical checks to ensure stability under all conditions. The design process itself is inherently more challenging and carries a higher risk of ending up with an unstable filter if you're not careful. The key takeaway is, IIR filters offer potential efficiency gains, but you must be meticulous about ensuring stability. And the other major trade-off is nonlinear phase response. Generally, standard IIR filters do not have linear phase. As we discussed with FIR filters, this means different frequency components get delayed by different amounts as they pass through the filter.
Which distorts the waveform shape.
Exactly. It can significantly distort the shape of the signal. While this might be perfectly acceptable for some applications, maybe you only care about the power in different frequency bands, like for simple power spectrum estimation, and not the exact waveform shape. But for applications like clinical ECG interpretation, where the precise morphology, the shape and timing of the waves is critical for diagnosis, this nonlinear phase distortion is a significant drawback. It can make interpretation difficult or even misleading.
So not ideal for looking closely at ECG shapes.
Typically not, no. Though there are advanced techniques to design IIR filters with approximately linear phase in the passband, it adds complexity. IIR filter design often starts by taking a known, well-behaved analog filter design, like Butterworth, Chebyshev elliptic filters, and using mathematical transformations, like the popular bilinear transformation, to convert that analog filter's transfer function into an equivalent digital IIR filter's transfer function. A classic application where IIR filters shine, despite the phase issues, is in creating digital integrators. Integration is fundamentally an IIR process because the current output, the accumulated sum, depends on the previous output. These are essential for tasks like calculating the area under a curve, in a signal perhaps to quantify the total energy in a muscle contraction burst, or the cumulative effect of some physiological response.
Like summing up the signal over time.
It's exactly. Simple examples include the rectangular integrator or the trapezoidal integrator. They offer different levels of accuracy in approximating true mathematical integration. Both these simple integrators actually have a pole right on the unit circle at z equal 1. representing zero frequency,
Mm.
which means they are marginally stable. They don't blow up, but their output can grow indefinitely if there's a DC offset in the input. A more complex one, like Simpson's rule integrator, provides an even better approximation of an ideal integrator, especially for lower frequencies. However, and this highlights the IIR challenges, something like the Simpson's rule integrator can dangerously amplify high-frequency noise near the foldover frequency, half the sampling rate. So, while efficient and accurate for clean signals, it could be disastrous if used in a highly noisy environment without proper pre-filtering.
So again, efficiency comes with cautions.
Always with IR filters, it's the prime example. IR efficiency often comes bundled with design challenges related to stability and potential noise amplification that you just don't face with FIR filters.
Okay, we've got the theory down now, sampling. AD, the basic filter operations, stability, and the two main families, FIR and IIR, with their pros and cons. Let's bring it all together. What does this all mean for actually using these filters in the real world, particularly when we're talking about health, medicine, and the human body? This is where it gets really fascinating, right?
This is indeed where the rubber meets the road, as they say. Digital filters are absolutely indispensable tools for cleaning, enhancing, separating, and ultimately interpreting the body's myriad electrical and physiological signals. They are truly the unsung heroes, quietly working inside so many medical devices, turning noisy, complex, raw data into accurate, actionable, often life-saving information for doctors and patients. Let's look at some common filter types and their crucial medical applications. We have low-pass filters. As the name suggests, they pass low frequencies and block or attenuate high frequencies.
Getting rid of high-frequency noise.
Exactly. They're crucial for removing high-frequency noise. This could be muscle contraction noise, EMG, as we mentioned, which often contaminates ECG or EEG signals. Or it could be random electronic noise from the sensors or environment. For instance, the standard bandwidth for a diagnostic clinical ECG is often defined as 0.05 Hz to 100 Hz. That 100 Hz upper limit is enforced by a low-pass filter because frequencies significantly higher than that in an ECG are almost certainly just noise, not meaningful cardiac activity. We want to see the heart signal clearly.
Makes sense. Cut out the fast static.
Then you have high-pass filters. These do the opposite. They pass high frequencies and attenuate low frequencies.
Getting rid of slow drift.
Precisely. They are essential for eliminating things like baseline wander or drift in signals like the ECG. This is a very common problem, especially in ambulatory monitoring where the patient is moving around. Breathing, slight electrode movement, it can cause the entire ECG trace to slowly drift up or down on the screen, making it hard to see the actual heart rhythm. A high-pass filter removes these very slow variations. For example, a monitoring ECG bandwidth might be 0.5 Hz to 50 Hz. That 0.5 Hz lower limit is set by a high-pass filter to cut out baseline drift below that frequency, stabilizing the trace without removing the important faster components of the heartbeat itself.
Okay, low pass for fast noise, high pass for slow drift.
You got it. Next are bandpass filters. These are designed to allow only a specific desired range or band of frequencies to pass through, while attenuating frequencies both lower and higher than that band.
So focusing on a very specific frequency range.
Exactly. They are vital for maximizing the signal-to-noise ratio, SNR, when you're trying to detect a specific feature that has most of its energy concentrated in a particular frequency band. A prime example is detecting the QRS complex in ECGs, especially for devices that only need to measure heart rate, like basic cardiotachometers. Such a filter might be precisely centered at around, say, 17 Hz, because that's where a lot of the QRS energy lies, and it might have a specific Q or quality factor, maybe around 3 or 4.
What does that Q factor mean?
The Q factor essentially tells you how narrow or selective the bandpass filter is. A higher Q means a narrower, sharper filter that lets through only a very tight band of frequencies. So this QRS detection filter would be tuned to perfectly target the dominant energy of the QRS complex, while effectively filtering out the lower frequency PNT waves, baseline drift, and higher frequency muscle noise. It zeroes in on the heartbeat signal.
Great for counting beats, but you lose the other details.
Absolutely. It's optimized for detection, not for detailed diagnostic interpretation of the full waveform. Then we have bandstop filters, also often called notch filters. These do the opposite of bandpass. They are designed to reject or stop a very narrow band of frequencies, while allowing all other frequencies, both lower and higher, to pass through relatively unaffected.
Like cutting out one specific annoying frequency.
Exactly. And their most critical application in medicine is removing 60 Hz line frequency interference, or 50 Hz in many parts of the world outside North America. This hum from electrical power lines and equipment is a major pervasive source of noise in almost all clinical environments. It can easily swamp faint biological signals.
I can imagine that drove early researchers crazy.
Oh, undoubtedly. Trying to get a clean EEG or ECG amidst that constant 60 Hz hum must have been a nightmare before good filtering. A simple and effective way to design a digital notch filter is by strategically placing mathematical zeros directly on the unit circle in the Z-plane, precisely at the angles corresponding to the frequency you want to eliminate. For example, to remove 60 Hz noise when your sampling rate is 180 samples per second, you'd place zeros at angles of plus minus 120 degrees, which is plus some 23 radians. This creates a sharp notch right at 60 Hz. It's like digitally tuning out that specific interference. Indispensable. We also use derivative filters. These aren't about passing or blocking frequencies in the usual sense, but rather about mathematically calculating the slope or rate of change within the signal.
Finding the steep parts of the wave.
Exactly. The slope is often a key feature for distinguishing different parts of a waveform. In ECG analysis, for example, differentiation helps accentuate the rapid upswings and downswings characteristic of the QRS complex. The QRS is typically much sharper, has steeper slopes, than the slower, more rounded P&T waves. Applying a derivative filter makes these sharp QRS features stand out even more clearly, making automated detection easier and more reliable. Examples range from simple 2-point difference filters to more sophisticated 3-point central difference, or even least squares polynomial derivative filters that fit a curve and find its slope. And finally, let's mention smoothing filters, often implemented as FIR polynomial filters. These are specifically designed to reduce sharp discontinuities and high-frequency noise, essentially making signals appear smoother and more continuous without drastically changing their overall shape.
Cleaning up jagged edges.
Precisely. They are particularly useful for post-processing signals that have been compressed using certain data reduction algorithms, like the EasyTech algorithm we might discuss later. These algorithms sometimes produce a reconstructed waveform that looks jagged or step-like. Applying a smoothing filter makes the data visually more acceptable for clinical review, removing those artificial sharp edges while preserving the underlying trend. It improves the aesthetic quality for interpretation.
That's a fantastic overview. Low pass, high pass, bandpass, notch, derivative smoothing, a whole toolkit. Let's take the ECG again, the absolute heartbeat of biomedical signal processing as our prime example. How do all these different filters actually come together in practice to make sense of your heart's electrical activity in a real clinical device?
The ECG is indeed the perfect illustration, because how we filter it depends entirely on what we want to learn from it. The processing requirements vary significantly depending on the clinical application. First, you have the clinical diagnostic ECG bandwidth, typically 0.05 Hz to 100 Hz, or sometimes even 150 Hz. This wide bandwidth is used for detailed diagnosis from a standard 12-lead ECG, recorded usually at rest. Here, doctors are looking for subtle morphological changes, tiny alterations in the shape, duration, or amplitude of T, QRS, and T waves. These subtleties can indicate ischemia, past heart attacks, conduction problems, electrolyte imbalances, and more. So both the very low frequencies, down to 0.05 Hz to see slow ST segment changes, and relatively high frequencies, up to 100 Hz or more to see sharp QRS features and potential late potentials, must be preserved. We need high fidelity here.
Maximum detail for diagnosis.
Maximum detail. Then you have the monitoring ECG bandwidth, often 0.5 Hz to 50 Hz, or maybe 40 Hz. This is used in settings like the ICU, telemetry units, or for ambulatory Holter monitors where patients are moving around for extended periods. Here, the bandwidth is intentionally restricted compared to the diagnostic ECG. The high-pass filter is set higher, 0.5 Hz versus 0.05 Hz, to more aggressively remove baseline wander caused by movement. The low-pass filter is set lower, 50 Hz versus 100 Hz, to significantly attenuate higher frequency muscle noise, EMG, which is much more common when patients are active.
So sacrificing some detail for robustness against noise and motion.
Exactly. The primary focus in monitoring is usually on detecting significant rhythm disturbances, or arrhythmias, like detecting if the heart rate is too fast, too slow, or irregular, rather than analyzing minute morphological details. Clarity for beat detection and basic rhythm analysis is prioritized over absolute waveform fidelity. And third, you have specialized filters for cardiotachometers, devices that only measure heart rate. For this specific task, a dedicated bandpass filter is often employed. As we discussed, one might be centered at, say, 17 Hz with a Q of 3 or 4. Its sole purpose is to maximize the QRS signal-to-noise ratio. It's designed to strongly emphasize the frequency components characteristic of the QRS complex, while aggressively filtering out the P waves, T waves, baseline drift, and noise.
Just isolating the R wave spike as much as possible.
Pretty much. It's highly effective for reliable beat detection, which is all you need to calculate heart rate. But importantly, this heavy filtering severely distorts the overall ECG waveform shape, rendering it completely unacceptable for any kind of clinical diagnostic interpretation based on morphology. It's purely for counting beats. Now, a classic and highly effective example that combines several of these filtering stages is the Pan and Tompkins QRS detection algorithm. It's a widely cited, robust method for real-time QRS detection, often implemented in monitors. It's a multi-stage digital filter cascade. 1. Bandpass filter. The first stage applies a bandpass filter, maybe centered around 10 or 17 Hz. This isolates the predominant QRS energy, attenuating the lower frequency PT waves and baseline drift, and cutting out higher frequency EMG noise and power line interference. It's doing noise reduction and feature emphasis simultaneously.
Okay, first pass cleanup and focus.
2. Differentiation. The filtered signal is then passed through a derivative filter. As we said, this enhances the high-slope portions characteristic of the QRS complex, making it stand out even more from slower waves. Up to this point, all the processing has been done by linear digital filters.
Highlighting the sharp peaks.
Full squaring. Now comes a crucial nonlinear transformation. Each point in the differentiated signal is squared. This does two things. It makes all the data positive, which simplifies later processing, and it significantly accentuates the higher frequency components within the signal that were emphasized by the differentiation step. Since the QRS is rich in these higher frequencies compared to noise or other waves, squaring further boosts its prominence.
Making the QRS peaks even sharper relative to everything else.
Exactly. 4. Moving window integration. The squared waveform then goes through a moving window integrator. This is essentially a smoothing filter that sums up the signal energy over a short time window, typically chosen to be about the width of a typical QRS complex, maybe 150 milliseconds. This stage integrates the area under the squared, differentiated peaks, providing a future waveform that gives information about both the presence and the duration or width of the QRS complex.
So it captures the whole QRS energy burst.
It captures that energy burst.
Sorry.
5. Thresholding. The final stage is clever. It involves using adaptive thresholds. Usually there are two sets. One for identifying potential QRS peaks in the integrated signal, and another, often lower threshold applied to the original filtered signal before squaring integration, to help distinguish true QRS complexes from high-sloped noise artifacts or tall T waves. These thresholds aren't fixed. They continuously adjust based on the recent history of detected peak heights and noise levels. This adaptivity makes the detector much more robust to variations in QRS amplitude and noise.
So it learns what a normal beat looks like for this patient right now.
In essence, yes. It adapts to improve sensitivity, detecting real beats, and specificity, rejecting false positives like noise or T waves. And as an added practical measure, especially important with patients who have pacemakers, there's often an analog circuit before the AD converter, or sometimes a digital preprocessing step designed to limit the slew rate, how fast the signal can change. This helps reject the very sharp, narrow pulses generated by pacemakers, which could otherwise be mistaken for QRS complexes by the algorithm.
Wow, that's quite a cascade. Bandpass, differentiate, square, integrate, threshold.
It is. It's a beautiful example of how multiple stages of well-chosen linear and nonlinear digital signal processing steps can be combined to create a highly robust and reliable system for extracting critical information in this case, detecting every single heartbeat accurately, even in the presence of significant noise. It really demonstrates the power and precision available with digital filtering in saving and improving lives.
Okay, we've covered a lot of ground on fixed filters, designing them for specific tasks. But what happens when the noise itself isn't constant? What if it's dynamic, maybe subtly shifting its characteristics over time, like maybe the 60 hertz hum changes slightly, or muscle noise comes and goes? Can a filter be, well, smarter? Can it be intelligent enough to learn and adapt to those changes in real time?
That's precisely where we unlock a whole new level of sophistication with adaptive filters. This is where it gets really interesting. These are truly intelligent systems. They're designed to continuously learn the characteristics of their processing environment, the signal, the noise, and then automatically change their own filtering properties, their coefficients, in an optimal way to achieve a specific goal, like minimizing noise.
So they adjust themselves on the fly.
Exactly. On the fly. This is genuinely remarkable because, unlike the fixed filters we've discussed, adaptive filters generally don't require detailed prior knowledge of the precise signal or noise characteristics. You don't need to know exactly what the noise looks like beforehand. Furthermore, they can track slowly varying statistics. So if the nature of the noise subtly changes over time, maybe the patient shifts position in bed, changing the electrode contact in the noise profile, or nearby equipment turns on or off, changing the electrical interference, The adaptive filter can adjust its parameters to continue suppressing the noise effectively.
That sounds incredibly powerful for real-world scenarios.
It is incredibly powerful. A classic model for understanding how they work is the adaptive noise canceller. Imagine you have a primary input signal. This contains the desired signal, like an ECG, but it's corrupted by noise. Then you also need a secondary reference input. This reference input ideally contains only noise, or at least noise that is correlated in some unknown way with the noise corrupting your primary signal. Maybe it's from a nearby sensor placed specifically to pick up the environmental noise, but not the physiological signal.
Okay, one input with signal plus noise, one with just correlated noise.
Right, the adaptive filter's job is to take that reference noise input and process it essentially, filter it to create the best possible estimate of the noise component that's interfering with the primary signal. It then subtracts this noise estimate from the primary input, signal plus noise. The output of this subtraction is the clean signal, but it's also used as an error signal. This error signal is fed back to continuously adjust the coefficients of the adaptive filter itself, driving the filter to become better and better at predicting and canceling the noise.
So the error tells the filter how to improve its noise estimate.
Precisely. It's a closed-loop learning system. The filter constantly refines its internal model of the noise based on how well it's currently canceling it. The most widely used algorithm for performing this coefficient adjustment is the least mean squares, LMS algorithm. It's popular because it's relatively simple computationally and quite effective. It works by iteratively adjusting the filter coefficients in a direction that minimizes the mean square value of that error signal, the output after subtraction. A critical parameter you have to choose carefully in the LMS algorithm is the step size, often denoted by the Greek letter mu. This controls how much the coefficients are adjusted at each step.
Like how big a step it takes in learning.
Exactly. If the step size is too large, the filter can become unstable. Its adjustments might overshoot, and the coefficients might bounce around wildly or even diverge. If it's too small, the filter adapts very slowly, and it might not be able to keep up with rapid changes in the noise characteristics. Finding the right balance is key to good performance.
A delicate tuning act.
It is. Now, the applications of adaptive filters in biomedicine are diverse and incredibly impactful. They're used, for example, for 60 Hz interference suppression, because the exact amplitude and phase of power line noise can fluctuate depending on loads on the line or nearby electrical activity. An adaptive filter can track these variations and cancel the hum much more effectively than a fixed notch filter, especially if the frequency drifts slightly.
Ah, so it handles variations better than a fixed notch.
Yes, and perhaps one of the most remarkable applications is fetal ECG extraction. The electrical signal from a fetus's heart, the FECG, is incredibly faint when measured non-invasively from the mother's abdomen. It's completely buried within the much larger electrical signal from the mother's own heart, the MECG. An adaptive filter can be used here ingeniously. You use an ECG signal recorded from the mother's chest as the reference input, containing primarily the MECG noise source.
Yeah.
The primary input is the abdominal ECG, containing both MECG and FECG. The adaptive filter learns to predict the maternal ECG component present in the abdominal signal based on the chest signal and then subtracts it out.
Leaving behind the tiny fetal signal.
Exactly. It digitally peels away the overwhelming maternal layer to reveal the hidden fetal heartbeat. It's an amazing application, crucial for non-invasive fetal monitoring. Other applications include cardiogenic artifact cancellation and impedance pneumography. This technique measures breathing by monitoring chest impedance changes. However, the beating heart also causes impedance changes due to blood flow and volume shifts, which can interfere with the breathing signal. Adaptive filters can model and remove these cardiac-induced artifacts, giving a clearer respiration signal. They're even used in sophisticated algorithms for ventricular fibrillation or tachycardia detection. Adaptive modeling techniques can try to estimate the locations of poles in the Z-plane corresponding to the frequency spectrum peaks or formants of the ongoing heart rhythm. The characteristics of these poles can help distinguish between normal rhythms and life-threatening arrhythmias like VF or VT, which have very different spectral signatures.
That adaptive filtering is really impressive. Learning on the fly. Okay, another challenge. What if the signal you're looking for is incredibly faint, almost completely buried in a mountain of random noise? Even adaptive filters might struggle if the signal is that weak relative to the noise. How do you find that whisper in a hurricane? How do you detect a tiny electrical event amidst a cacophony of biological and environmental static?
That's precisely the challenge that another powerful digital technique, signal averaging, is designed to overcome. It's specifically suited for situations where you have a repetitive signal, a signal that occurs over and over again in a similar pattern that is obscured by random, uncorrelated noise. And the beauty is, it can pull that signal out of the noise, often without introducing significant signal distortion, unlike some types of filtering.
So it works if the signal repeats, but the noise is random.
That's the key requirement. The signal must be evoked or occur repeatedly, and you need a reliable way to time align each repetition. The noise needs to be random and ideally uncorrelated with the signal and with itself from one repetition to the next. The mechanism hinges on the fundamental difference between how repetitive signals and random noise behave when you sum them up over time. When you take multiple time segments, or epochs, each containing one repetition of the signal plus noise, and you precisely align them based on a consistent timing reference point, a fiducial point, like a trigger stimulus or a detected R wave, and then you average them together point by point. The signal components, being essentially the same in each epoch and perfectly aligned, add up constructively. They reinforce each other. After averaging m repetitions, the signal amplitude in the average remains roughly the same as the original single epoch signal amplitude. It doesn't grow with m in the average, unlike simple summing.
Okay, the signal stays consistent in the average.
Right, but the random uncorrelated noise components, which are different in each epoch, sometimes positive, sometimes negative, averaging around 0, tend to cancel each other out as you average more and more epochs. Mathematically, the RMS, root mean square value, or the standard deviation of the noise, decreases by the square root of the number of averages. So the noise level goes down as one error.
Signal stays the same, noise goes down.
Exactly. The impressive result is that the signal-to-noise ratio, SNFR, the ratio of the signal strength to the noise's strength, improves by a factor of the square root of MR. So if you average, say, 100 repetitions, M100, the SNR improves by a factor of set 100, which is 10. If you average 1,600 repetitions, the SNR improves by a factor of 40. This allows incredibly weak signals, initially completely invisible in the noise, to emerge clearly.
That's a huge improvement. Where is this used?
A crucial clinical application is the detection of late potentials in ECGs. These are very tiny, high-frequency electrical signals that occur right at the very end of the QRS complex. They are thought to represent areas of slow conduction in the heart muscle, often resulting from scar tissue after a heart attack. These late potentials are normally completely hidden, totally invisible in the noise of a standard single-beat ECG recording. By recording many heartbeats, carefully aligning them using the main R-wave peak as the fiducial point, and then averaging hundreds or even thousands of these aligned beats, signal averaging allows these minuscule late potentials to emerge from the noise.
And finding them is important.
Yes. Detecting late potentials can be diagnostically significant, as their presence is associated with an increased risk of developing dangerous ventricular arrhythmias in the future. Signal averaging makes this non-invasive risk stratification possible. It's also widely used in evoked potential studies, like auditory or visual evoked potentials in neurology, where the brain's response to a stimulus is extremely small compared to background EEG noise. It's interesting to think about signal averaging in the frequency domain, too. It acts like a comb filter. Imagine a comb. It has teeth separated by gaps. A comb filter in the frequency domain has passbands, the teeth, centered at the fundamental frequency of the repetitive signal in all its harmonics, integer multiples. It strongly attenuates frequencies that fall in the gaps between the teeth.
So it passes the signal's frequencies, but rejects noise in between.
Precisely. As you increase the number of sweeps, you average. The teeth of this comb filter become narrower and sharper. This allows the filter to become more and more selective, passing only the signal's harmonic components while rejecting more and more of the random noise energy that falls between those harmonics. Now, signal averaging isn't magic. It does have limitations. It relies on the assumption that the noise is truly random, Gaussian, and uncorrelated from epoch to epoch. If there's some underlying coherent noise that's also time-locked to the trigger, it won't average out. And perhaps the most critical practical challenge is accurate alignment. You need a very precise and stable fiducial point to align each waveform repetition. Even slight timing jitter or inconsistency in aligning the epochs can act like a low-pass filter, smearing out the high-frequency components of the average signal and potentially distorting the very features, like late potentials, you're trying to uncover. Careful alignment is absolutely paramount.
Okay, signal averaging for pulling repeating signals out of noise. Very cool. Now, let's say we've done all this fantastic filtering, maybe even adaptive filtering and signal averaging. We've got our beautiful, clean signal. But what if it's still just too much data? especially for long-term monitoring like a 24-hour Holter ECG recording or transmitting data wirelessly from a wearable sensor. Storing or sending gigabytes of raw data isn't always practical. We need to make these signals more manageable, right?
Absolutely. This brings us to the crucial area of data reduction or data compression techniques. They're absolutely vital for managing the sheer volume of data generated by modern biomedical monitoring, especially for long-term recordings or remote transmission, where storage capacity and bandwidth are limited. The goal is to reduce the amount of data significantly while preserving the essential diagnostic information. There are several different approaches, ranging from simple and fast to more complex but potentially more efficient. Let's explore a few key algorithms mentioned in Tompkins. One simple, fast method is the turning point, TP, algorithm. The concept is straightforward. It selectively discards exactly half of the originally sampled data points. It works by looking at 3 consecutive points at a time. If the middle point represents a change in slope direction, a turning point like a peak or a valley, it's kept. If the middle point lies roughly on a straight line between its neighbors, no significant slope change, it's discarded.
So it keeps the peaks and valleys, throws out points on straight lines.
Essentially, yes. It provides a fixed, guaranteed 2.1 reduction ratio. It's computationally very cheap and fast. However, the reconstruction involves simply connecting the kept points with straight lines. This introduces some short-term time distortion, although this distortion is often not visually apparent on standard clinical monitor displays. A key limitation, though, is that if you apply it repeatedly, or if you apply it to wide bandwidth signals, you can start to seriously violate the original sampling theorem requirements, potentially losing important high-frequency details and making the reconstructed signal less clinically acceptable for fine diagnostic purposes. It's simple, but maybe crude for high-fidelity needs.
Quick and dirty 2.1 reduction.
Pretty much. A more sophisticated and widely used technique is AZTEC, amplitude zone time epoch coding. AZTEC works quite differently. It aims to decompose the raw signal into a sequence of horizontal lines, plateaus, and sloping lines, creating a piecewise linear approximation of the original waveform. It does this by defining an amplitude tolerance band. As long as the signal stays within that band, it's represented by a horizontal line, a plateau defined by its level and duration. When the signal moves outside the band, the algorithm determines the best fit sloping line to represent that segment until the signal potentially levels off again.
So it approximates the wave with flat bits and angled bits.
Exactly. It only stores the parameters needed to define these plateaus and slopes, like starting level, duration, slope value. This algorithm offers a variable reduction ratio, which often achieves much better compression than TP, frequently 10.1 or even higher, depending on the complexity of the signal and the chosen amplitude tolerance threshold. Simpler signals compress better.
Higher compression, but what's the catch?
The catch is in the reconstruction. When you reconstruct the signal from the stored AZTEC codes, you get a waveform that looks very step-like or jagged because of the piecewise linear approximation. While it captures the main trends, this jagged appearance is often considered clinically unacceptable for visual review. Therefore, AZTEC compressed data usually requires post-processing with a smoothing filter, like one of those FIR polynomial filters we mentioned, to remove the sharp corners and make it look more like the original physiological signal. However, this post-smoothing step itself can introduce some amplitude distortion or potentially filter out fine details, so there's a trade-off between compression ratio and fidelity.
Smoothed, but maybe slightly distorted.
Potentially, yes. Another adaptive approach is the FAN algorithm, sometimes called SOPA, scan-along polygonal approximation. The FAN algorithm works by defining an error fan, 2 diverging lines originating from the last stored data point. As long as subsequent data points fall within this fan, they are considered redundant and discarded. The algorithm only stores the next sample point when it falls outside the fan's boundaries. That point then becomes the origin for a new fan.
So it only keeps points that deviate significantly from the current trend.
That's the idea. It adaptively determines which points are truly significant for defining the waveform's shape within a given error tolerance, defined by the fan angle. It can achieve good reduction ratios, sometimes comparable to or better than AZTEC, while potentially maintaining better waveform fidelity for certain types of signals because it follows the curve more closely than AZTEC plateaus and slopes might. Now, the methods we've discussed so far, TP, AZTEC, FAN, are generally lossy compression techniques. That means the reconstructed signal is not exactly identical to the original. Some information is lost in the process.
You can't get the original back perfectly.
Correct. But there are also lossless data compression algorithms, where you can perfectly recover the original data without any loss of information. A classic example used in biomedical signal processing is Huffman coding. Huffman coding is clever. It works by first analyzing the statistics of the quantized data samples. It recognizes that some amplitude values occur much more frequently than others. It then assigns variable-length binary code words to each possible amplitude value. Shorter code words are assigned to the more frequent values, and longer code words to the less frequent values.
Like Morse code for data values. Common letters get shorter codes.
Exactly like that. It's the same principle. By using shorter codes for the commonest data values, the average code length per sample is reduced, leading to overall data compression. Because there's a unique code for each value and a defined way to parse the bit stream, you can decode it and perfectly reconstruct the original sequence of data samples. Lossless.
Perfect recovery, but how much compression do you get?
The compression ratio achieved by Huffman coding depends entirely on the statistical distribution of the source symbols, how uneven the probabilities are. If some values are vastly more common than others, you get good compression. If all values are roughly equally likely, you get very little compression. It also requires transmitting or storing a translation table, the Huffman tree or codebook, along with the compressed data, which adds some overhead, especially for shorter data segments. A key limitation is its sensitivity to transmission errors. A single flipped bit in the compressed stream can cause the decoder to lose synchronization, potentially scrambling all subsequent data until a reset point. Finally, a technique that often combines well with Huffman coding is residual differencing. The idea here is clever. Instead of directly compressing the raw signal samples, you first try to predict the next sample based on previous ones, or maybe based on an average template. Then you calculate the difference between the actual sample and the predicted sample. This difference is called the residual.
So you compress the error, the part the prediction got wrong.
Exactly. Often this residual signal has a much narrower amplitude range and a statistical distribution that's more peaked around 0 compared to the original signal. This makes the residual signal much more amenable to efficient compression using techniques like Huffman coding. For ECG compression, for example, one approach is to calculate an average beat estimate for the patient. Then, for each detected heartbeat, you subtract it from this average template to get a residual beat. This residual, representing the beat-to-beat variations, is then entropy coded, like with Huffman, and stored and transmitted, along with information about the beat locations and the average template itself. This can achieve very high compression ratios for relatively stable ECG signals. It focuses on efficiently coding the differences or innovations in the signal, rather than redundantly coding the highly repetitive parts.
Wow, okay. We've covered filtering theory, common filter types, adaptive filters, signal averaging, and even data compression. But all these sophisticated algorithms, the intense calculations for filtering, the constant adjustments in adaptive systems, the complex coding for compression, they must demand incredible computational horsepower, especially to happen in real time. What kind of specialized chips, what kind of hardware makes all this real-time processing possible? How do we get these algorithms off the whiteboard and into actual medical devices?
That's where digital signal processors, or DSPs, come into the picture. This is the hardware that makes it all happen. DSPs are essentially specialized microprocessors. They are explicitly designed and architected from the ground up to perform the repetitive, numerically intensive calculations needed for signal processing tasks much more efficiently than a general-purpose CPU found in your typical computer.
So they're not like the chip in my laptop, they're optimized for signal math.
Exactly. Think of them as highly focused athletes, specifically trained for the mathematical marathon of signal processing. Whereas a general-purpose CPU is more like a decathlete, good at many different things, but maybe not world-class at any single event. The distinction is important. General-purpose CPUs are designed to run operating systems, manage complex software, handle diverse input-output. They need versatility. DSPs, on the other hand, are optimized architecturally for a relatively limited set of core functions, primarily those storage, delay, multiplication, and addition operations we identified earlier as the fundamental building blocks of digital filters. They're designed to perform these operations, particularly multiply-accumulate operations, extremely quickly and often in parallel.
MAC operations, multiply and accumulate.
Yes, the multiply and accumulate MAC operation is central to digital filtering, multiplying a sample by a coefficient and adding it to an accumulator. DSPs often have dedicated hardware MAC units that can perform this entire operation in a single clock cycle, something a general-purpose CPU might take multiple cycles to achieve. Because of this specialization, DSP performance is often benchmarked not just by general MAPs, million instructions per second, or MFLOPS, million floating point operations per second, but specifically by their MAC rate,
how many of these they can do per second, as this metric directly reflects their core strength in executing signal processing algorithms. The history here is interesting, too. The first commercial single-chip DSPs started emerging in the early 1980s from pioneers like Bell Labs, Texas Instruments, with their very influential TMS-320 family, NEC, and Intel. Later generations like the Motorola DSP 56001 from the late 80s showcased advanced features like highly parallel and pipelined architectures. They might have multiple data buses, multiple memory banks allowing simultaneous access, hardware support for loops and address generation, and of course, those fast hardware array multipliers and multiple arithmetic logic units, ALUs, all geared towards executing those core DSP algorithms as fast as possible.
So the chip architecture itself is tailored for filtering math.
Absolutely. This dedicated architecture allows them to achieve the real-time processing speeds demanded by complex biomedical applications, things like instantly analyzing an incoming ECG stream, processing a complex ultrasound image in real time, or running sophisticated algorithms inside a digital hearing aid.
That specialized architecture sounds powerful. But how do engineers manage to pack so much processing might, all those multipliers and memory banks, onto a tiny piece of silicon? It must be related to Moore's law again, right? The advances in actually manufacturing the chips.
Precisely. It all comes back to the incredible advancements in semiconductor manufacturing technology, specifically VLSI, which stands for Very Large-Scale Integration. VLSI is the technology, the process that allows engineers to place millions and now routinely billions of microscopic transistors onto a single integrated circuit, a single chip.
Packing more and more stuff into the same small space.
Exactly. This incredible density is what has enabled the development of the high-performance DSPs we just discussed. It's also driven the development of increasingly specialized hardware designs, sometimes called algorithm-based architectures or algorithm-specific architectures. Because VLSI makes it feasible to put so much functionality on one chip, designers can create architectures that are even more tightly tailored to executing specific types of DSP algorithms with maximum efficiency, going beyond even general-purpose DSPs. These advanced architectures leverage several powerful techniques to maximize computational throughput. We already mentioned parallel processing or multiprocessing, using multiple processing units working concurrently. This includes concepts like SIMD, single instruction, multiple data, where a single instruction operates on multiple data elements simultaneously. Imagine applying the same filter coefficient multiplication to 4 different input samples all at once. Very efficient for array or vector operations common in DSP, MIMD, multiple instruction, multiple data, or multiple processors execute different instruction streams on different datasets concurrently. This offers more flexibility and is common in complex tasks like image processing, where different parts of an image might undergo different processing steps simultaneously.
Doing more things at the same time.
Yes. Another key technique is pipelining. You can think of it as an extension of multiprocessing, or like an assembly line for calculations. It breaks down a complex operation, like a mathy operation, which involves fetching data, multiplying, adding, storing, into smaller sequential stages. Different stages can then work on different data samples simultaneously. While one sample is being multiplied, the next sample is being fetched, and the previous sample's result is being stored, all overlapping in time. This keeps all parts of the hardware busy and dramatically increases the overall throughput, the rate at which results come out.
Like a factory assembly line for numbers.
Yeah, a perfect analogy. Then there are architectures like bit serial processing. Instead of operating on entire data words, like 16 or 32 bits at once, bit serial architectures perform operations only 1 bit of a word at a time. This might sound slower, but it significantly simplifies the required hardware. Adders and multipliers become much simpler, and dramatically reduces the amount of wiring needed to interconnect components on the chip, as well as the number of input-output pins. This simplification can facilitate easier design and layout, especially for very complex, dense chips, and sometimes the overall throughput can still be very high due to massive parallelism.
Simpler hardware, easier to connect.
Right. And building on that idea are systolic arrays. These often combine bit serial processing with pipelining in a highly regular array-like structure. Data flows rhythmically and systematically, hence systolic, like the pumping of the heart, through an array of simple identical processing elements, PEs. Each PE performs a small part of the overall computation and passes its result to its neighbor. Data and partial results are continuously pumped through the array. Systolic arrays are incredibly well suited for VLSI implementation because of their simple, regular, and modular structure with only local interconnections. They are extremely efficient for specific, highly structured computations like matrix multiplication, convolution, which is core to FIR filtering, and correlation.
Data flowing through a grid of simple processors.
That's a good way to picture it. Now, the impact of these VLSI-based DSP architectures on actual medical applications is enormous and continues to grow. Digital hearing aids are a prime example of VLSI's power. Modern hearing aids are tiny marvels containing sophisticated DSPs. VLSI allows them to implement complex filtering algorithms entirely in software. This offers extreme flexibility. An audiologist can precisely tailor the frequency response and compression characteristics to compensate for an individual's unique pattern of hearing loss, just by programming the DSP. It also allows for advanced features like adaptive noise reduction and feedback cancellation. This software-based approach means greater reliability, no analog components to drift, and a much simpler, more accurate fitting process compared to older analog hearing aids.
Customizing the sound perfectly for the user.
Exactly. And think about portable medical instruments. The relentless progress of VLSI leading to higher density, significantly lower power consumption, and reduced cost per function is the engine driving the continuous improvement and miniaturization of devices like portable arrhythmia monitors, Holter monitors, implantable defibrillators, glucose monitors, pulse oximeters, and countless other advanced medical devices. VLSI enables sophisticated processing to happen right there on the patient, allowing for continuous, unobtrusive health monitoring and faster diagnostics. When engineers are designing these instruments, they face choices. They can use readily available off-the-shelf DSP chips, which offer good performance and faster time to market. Or, for higher volume products or very specific performance needs, they might design an ASIC, application-specific integrated circuit, which is a chip custom designed for one particular application, offering better optimization but higher upfront design costs. Or in some cases, they might go for a fully custom chip design. Each choice involves balancing design time, development cost, performance requirements, power consumption, and flexibility, ultimately determining the capabilities and feasibility of the next generation of life-enhancing medical technology. Hashtag outro.
So, after all that, what does this really mean for us? We've taken quite a journey today, haven't we? From raw, noisy physiological signals coming off the body, all the way to precise, clean, actionable insights. And it's all thanks to this incredible, often invisible world of digital filter design. We've seen how tiny transistors, relentlessly following Moore's law, combined with clever algorithms built from just those three basic operations, delay, multiply, add, can literally help us hear a fetal heartbeat through the noise, diagnose complex heart conditions from subtle ECG changes, and generally make sense of the overwhelming symphony of electrical and physiological signals produced by the human body. It really is a testament to human ingenuity, isn't it?
It truly is. And considering the ongoing, seemingly unstoppable advancements in digital processing power, coupled with our ability to capture increasingly complex and high-volume biomedical data from more sources than ever before, it really raises a profound question for all of us, I think. How will our fundamental understanding of human physiology, health, and disease continue to be transformed as these digital eyes and ears become ever more sensitive, more intelligent, more adaptive, and more deeply integrated into healthcare and even our daily lives? What completely new aha moments, what diagnostic breakthroughs await us as that line between the biological signals themselves and their sophisticated digital interpretations continues to blur? It feels like we're potentially on the cusp of revolutionizing diagnostics and personalized medicine in ways we can only just begin to imagine.
That's a fantastic thought to end on. The next time you see a patient monitor in a hospital room, or maybe even just glance at your fitness tracker sensing your pulse, take a moment to remember these silent, powerful digital filters working tirelessly inside. They're constantly sifting through the noise, pulling out the patterns, cleaning up the data, bringing clarity to complexity, all to help us understand ourselves better, stay healthier, and ultimately, in many cases, to save lives. Thanks for joining us on this deep dive. We'll catch you next time.